Hi. So today I want to talk about transmission electron microscopy. And the father of transmission electron microscopy is Ernst Ruska, pictured here in this photograph with one of his later prototypes of the TEM, or a later commercial model of TEM. He was the inventor in the years 1932 to 1933. He came up with the concept and developed a prototype of the TEM. And then he received his PhD for this work, and then after his invention, he worked in the field of electron optics to help develop commercial TEMs. And the first commercial TEM went on the market in 1939. Here he is with the later model. He shared his Nobel Prize with Binnig and Rower, who developed the scanning tunneling microscope, or STM, in 1986. Binnig and Rower got half the award, and then he got half the award. So Binnig and Rower each got a quarter, I guess. So here's his baby. This is a schematic of a typical transmission electron microscope. There are things about TEMs and SEMs that are similar, and I'm going to highlight those, but I'll also point out when there's differences between the two types of microscopes so you can understand the distinctions. All right, so this is similar in electron microscopes. You have an electron gun here at the top. The simplest form of the electron gun would be a tungsten filament, where you have a wire, basically a tungsten wire that's bent into a sharp tip, and then you pass a current through that wire, and the wire heats up, and then the electrons are kicked off due to their thermal energy. This is called thermionic emission, okay? So that's the most common. There's other kinds of filaments, and for a more in-depth discussion of the optics of TEMs, SEMs, and other advanced microscopies, I really suggest you take our electron microscopy course. But once the electrons are created via thermionic emission in a tungsten filament TEM, they're accelerated from the cathode to the anode by a high voltage. Now, in a scanning electron microscope, this voltage is on the order of, say, up to 30,000 volts in a typical SEM. In a typical TEM, the voltage is a factor of 10 higher, okay? So typical TEMs have voltage ranges that go from, say, 100,000 volts to 300,000 volts, all right? Now, the reason that the accelerating voltage in a TEM has to be higher is because you have to accelerate those electrons through the sample, okay? It's a transmission electron microscope. So the electrons have to penetrate through the sample and come out the other side in order to form a bright field image. All right, so the electrons are accelerated away, and then they move down the column. The first thing they encounter is the condenser lens here. Now, the lenses in SEMs and TEMs are basically the same idea, okay? They're electromagnetic lenses. You pass currents through the lens, and then that generates a magnetic field. And through the Lorentz force law, F is equal to QV cross B, that steers the electrons and forces them to condense to form a probe. Now, in an SEM, what happens is that probe is focused to a spot on the sample, and then you raster that spot across the sample, and then you look at any signal that emerges from the sample as a result: secondary electrons, backscattered electrons, X-rays, whatever, okay? The magnification in an SEM is controlled by how much you scan the beam, okay? So each point or pixel is basically one interaction of the beam with that spot on the sample, okay? And the ultimate resolution of the SEM is controlled by how small you can make that spot. In a TEM, however, the magnification is controlled by how big an area is illuminated on the sample, all right? So the condenser lens focuses that beam down to some size, whatever size is desired, and then that beam passes through the sample, all right? So instead of generating your image point by point, it's kind of generated all at once as the beam passes through the sample. In this way, it's a little bit more like, say, a transmitted light optical microscope that you might see, where you have the light coming up through the sample, and then the optics focus that image that's generated when the light moves through the sample. So it's very similar in that way. You can also kind of think of an overhead projector, if you would. All right. So the condenser lens focuses the beam down. The beam passes through that sample. Most TEMs have a load lock here on the side where you load your sample in. Because the beam has to go through the sample, the samples have to be really thin, maybe 100 nanometers max thickness, okay? This means that sample preparation for transmission electron microscopes is usually a lot more intense than it is for scanning electron microscopes, okay? For a conductor or a semiconductor in a scanning electron microscope, for example, you could stick something in and generate an image as long as it wasn't dusty or oily or something. You could stick something in and get some kind of image. Maybe you'd have to do something a little bit more to get a nice image, but you could get something out of it, right? In a transmission electron microscope, that's not the case. There's whole courses where people learn how to prepare samples for microscopy, especially in biology where sample preparation techniques take up a lot of time, okay? So basically you have to slice really thin sections of your sample off if it's a bulk sample. And if it's something like nanoparticles, for example, they have to be also carefully prepared. Now, the samples are mounted on these little copper grids. They're tiny, they're about 3 millimeters across, and then they're loaded in special holders into the side. All right? Now, that's kind of a really quick, brief overview of the samples. Like I said, there's whole courses. But once the electron beam passes through the sample, then the objective lenses focus that beam that comes through, kind of similar to the optics on a transmitted light optical microscope. Okay? So it focuses the beam that comes through the sample, and then there's a projector lens that magnifies that image and focuses it below in some way. Okay, there's different kinds of ways to display the image depending on how old your TEM is. That might control it a little bit too, but there's fluorescent screens that glow when the electron beam hits it. There's photographic film, that's for the old school TEMs, and then there's a CCD camera that allows you to get your electronic image data out of it. Okay, so that's TEM basics. Now, the most common mode of operation for a TEM, the most common way to get an image, is called a bright field image. All right. In that, the electrons that pass pretty much straight through the sample, okay? They can be either totally transmitted or forward scattered, basically. Those go into forming the bright field image, all right? Remember that when electrons go through a sample or interact with the sample, they can also be reflected or scattered at high angles, and those would not appear in the bright field image, all right? So the transmitted electrons form that bright field image, and so what that means is that thicker regions of your sample, regions that have a higher atomic number, for example, gold has a higher atomic number than carbon, or areas of your sample that have a higher density, those are going to appear darker, all right? And then the areas on your sample where the electron beam passes straight through, basically, those appear very, very bright, right? So here's a typical looking bright field image. I borrowed this one from some students in the UK that are making gold nanoparticles for a class project, and then they imaged their gold nanoparticles, and it's a nice TEM image, okay? The image that forms, as you can see from this example, are basically 2D projections of your sample. Remember that in a scanning electron microscope, you can get some shading effects, okay? So the images often appear a little bit more like black and white photos, where you can kind of guess at what the three-dimensional view of the sample looks like. Not so much in a typical, regular old TEM bright field image. Now, there are ways, more advanced techniques, that you can generate 3D images in a TEM, but that's not your typical bright field image, and those take a lot more work than just the quick image that you see taken here, okay? Now, the ultimate resolution of the TEM is dictated by the wavelength of the electrons. This isn't the same as in an SEM, okay? In an SEM, the ultimate resolution, or the smallest pixel that you can really, resolve, is the size of the spot. Okay, so say in a typical SEM you focused your beam spot down to a nanometer or a few nanometers. That's your ultimate resolution. In a TEM, you're really limited by the wavelength more than anything else. That's the dominating term. Now, to give you a little history and some reminders on how this works, if you've forgotten your modern physics, Louis de Broglie was the French physicist that came up with the concept of matter waves, which is the foundation for all of quantum mechanics. He won a Nobel Prize for his prediction of the wave nature of the electrons that he came up with in 1924. He postulated that because photons have both wave and particle characteristics, people knew about the wave-particle duality of light from the photoelectric effect, for example, along with diffraction of light, which exhibited the particle and wave natures, respectively, of light. He postulated that if light can have a wave and particle nature, that matter can as well. And he came up with a formula for what the wavelength of a matter wave would be. The wavelength lambda is equal to Planck's constant h, 6.626 times 10 to the minus 34 joules seconds, divided by the momentum of the particle. Now, classically, the momentum of the particle would be the mass times its speed, okay? So you have lambda is equal to h over mu, where m is the mass and u is the speed. This is for classical particles, or classical speeds, I guess I should say, that are traveling at a small percentage of the speed of light. However, in a TEM, you're accelerating the electrons with very high voltages, and so they can get up to relativistic speeds that are a decent fraction of the speed of light. Let me give you an example of how that would go. Let's say that you accelerate an electron with a very high voltage in a TEM. Oops, excuse me. And that high voltage is about 300,000 volts, okay? Now, that would mean that your kinetic energy of your electrons would be 300,000 electron volts. And then to figure out what the speed is, we would use the equation for the kinetic energy, the relativistic kinetic energy, also from Modern 1, by the way, which is gamma minus 1 mc squared. Okay? Now, the mass energy of an electron is 511,000 eV. Okay? So now we can solve for gamma, and gamma is 1.59, which is a pretty decent gamma, really, if you remember your modern physics. We can use the formula for gamma and solve for our speed v. Gamma is equal to 1 over the square root of 1 minus v squared over c squared. And solving for v, we find that the velocity is 78% the speed of light, so that's going at a pretty good clip. Now let's plug that back into the equation for the wavelength for a de Broglie matter wave. So you have lambda is equal to h over gamma mu when it's a relativistic particle. So h, 6.626 times 10 to the minus 34 joules seconds, divided by gamma, 1.59, divided by the mass of an electron, 9.11 times 10 to the minus 31 kilograms, divided by the speed, which is 78%, or 0.78 of the speed of light, which is 300 million meters per second. Solving for that, you get a wavelength of 2 times 10 to the minus 12 meters, okay? So this would be the, sort of limiting factor or ultimate limit of your TEM that you could achieve with that wavelength. Now, there are limitations. So, for example, the real resolution of any kind of microscope was postulated by Abbe in 1873. So he postulated that the best resolution obtainable with a microscope is limited by the wavelength of the photons that are being used to probe the sample, lambda, and also the numerical aperture of the system, NA, okay? And it's going to be proportional, that resolution is going to be proportional to lambda divided by the numerical aperture. Now, at the time in 1873, they didn't know anything about matter waves, and so they thought that they would never be able to resolve at distances smaller than the wavelength of ultraviolet light. Okay. However, pretty much as soon as de Broglie came out with his postulate on matter waves, and Davison and Germer proved experimentally that they were true, as soon as Ruska heard about it, he immediately realized the possibilities for the electron microscope and started developing a prototype. Now, if you're wondering what the numerical aperture is, if you haven't had any optics, basically the numerical aperture is a dimensionless number that characterizes the range of angles over which a lens can transmit light. Now, in a transmission electron microscope, this was mainly be controlled by the geometry of your column. So the closer you put this little aperture or pinhole that the electron beam has to put through, the closer you put that to your lens, the larger that angle becomes. And then the larger angles give a larger numerical aperture and hence a higher resolution to your microscope. So when you design your TEM, you're controlling its resolution by the geometry of where you place things in the column. Just to show you, here's an image from your text, Nanoscience and Nanotechnology. But there's 3 different lens configurations that kind of illustrate why the numerical aperture would be controlled by the geometry. So the closer you have that aperture to the sample, the larger the area enclosing that lens becomes. And so for an angle subtended of 40 degrees, you get a numerical aperture of 0.64, and for 60 degrees, you get a numerical aperture of 0.87. So you can see your numerical aperture goes up as your angle goes up, and that controls the ultimate resolution. Okay. So what is a typical TEM resolution? Well, if you buy a more standard TEM, a resolution of 0.2 nanometers is pretty typical. Okay. Now, there's other things that do control the resolution of the TEM other than the numerical aperture and the wavelength, okay? And those are the aberrations or defects in your electromagnetic lenses. So if you can correct those defects or aberrations, then you can get your resolution closer to the theoretical limit. And this can be done. There's microscopes on the market right now that have resolutions of about 0.05 nanometers, but that is super not cheap. And you can only find those aberration-corrected TEMs at places with a lot of money, quite frankly, to devote to electron microscopy, with the top-notch researchers that can write those great NSF grants or DOE grants or what have you that sort of snag those high-dollar microscopes. And you can see how the resolution of TEMs have gone with time. Okay, so here's Ruska's first TEM way back in 1932, 1933, and that was better than the optical microscopes of the time. And then you can see that as he started to work on TEMs and lots of others developed those electron optics, made them better and better, then the resolution sort of appeared. And then it kind of started to plateau, and then another breakthrough was made with the aberration-corrected TEMs. Okay. So you might be going, aberrations, what kind of aberrations? Well, there's a bunch, all right? So there's 4 main ones. So the 2 pictured on this slide are spherical aberrations and then aperture diffraction. Okay, so first the spherical aberration. A spherical aberration in a lens is when you have a larger angular deflection for the electrons or waves that are further from the axis of the beam, then they get deflected further. They get deflected more than the electrons or waves that are closer to the beam axis. And what this does is it creates a disk rather than a point that the electrons are focused to. And then that disk, of course, limits your resolution. The size of the disk limits your resolution. So that's the spherical aberration. And it's one of the most important things to correct in electron optics, to get those aberration-corrected TEMs. Another kind of aberration is that when you put a wave through a pinhole, then it's going to form a diffraction pattern. And that's pictured here. Okay, now the electron microscope has a series of pinholes or apertures that the beam has to pass through. So there's diffraction occurring all along the column. Okay, so that can also change your resolution. Here's some more lens type aberrations. This is a chromatic aberration. This is also something that they worked pretty hard on when they were creating those aberration-corrected TEMs. What a chromatic aberration is that when the electrons are generated at the gun, there's actually a spread in energies of those electrons. The electrons created at a tungsten filament, for example, have a very high, compared to other guns, spread in energies. All right, so they have some spread in energy, say delta epsilon. There's other kinds of guns, like field emission guns, that have an energy spread that's much narrower. Now that's called a chromatic aberration, chromatic for color or wavelength, because the spread in the energies, of course, changes the speed of the electrons, and this change in the speed of the electrons changes the wavelength of the electrons. And of course, that controls the speed of the electrons, controls how much they're going to be deflected by those electromagnetic lenses. Remember, F is equal to QV cross B, where V is the speed or the velocity, okay? And so that changes the focus of the electron beam. All right, which changes how well you can image. All right, so what they've done in those aberration-corrected TEMs is they've worked really hard to select out specific wavelengths of electrons in a very narrow energy band, and that helps eliminate that type of defect. And then finally, we have the astigmatism. And astigmatism is when in a lens the waves are bent more along one axis, say the x-axis, than they are along another axis, say the y. Okay? And that creates, instead of a circular spot that the beam is focused to, kind of an oval. All right. Now this is relatively easy to fix. There's astigmation correction in SEMs and in TEMs. So this one we can do a little bit more about than some of the others. All right. So those are some of the common defects and also what help limit the resolution in TEMs. But like I said, the ultimate resolution now for a lot of these microscopes is on the order of 0.05 nanometers. So that's really, really good. Okay, so we've talked about bright field images. Let's talk about other imaging modes and the physics and explanation behind them. So remember that the experimental proof of de Broglie's wave hypothesis for electrons was carried out by Davison and Germer at Bell Labs in 1926. And they said, well, if particles have a wave nature, then under the correct conditions they should have diffraction, okay? And so what they did was they measured the wavelength of the electrons with a diffraction of those electrons from a nickel crystal, providing experimental confirmation to the idea of matter waves. Now, just to go over it, what they did was they created the electrons through thermionic emission. That should sound familiar. And they accelerated them with a voltage of 54 volts, calculated what the wavelength of those electrons should be based on de Broglie's hypothesis. They then struck a nickel target with that, and then they had a detector here off to the side where they measured the intensity of the beam that was measured at various angles. Okay, now remember that the Braggs had already come up with a theoretical prediction for the diffraction of X-rays at this time. And so Davison and Germer said, well, matter waves should be basically the same thing. Our geometry is slightly different. So here's the geometry for the Bragg sort of crystal diffraction, and here's the geometry for the Davison and Germer experiment. But although the geometry changes the formula a little bit, the idea is still there and very concrete. And so they predicted what the maximum intensity of the diffraction beam should be based upon the wavelength postulated from de Broglie's theory using the equation d sine phi is equal to n lambda. And then they knew what the crystalline lattice spacing in nickel was, 0.215 nanometers, so that allowed them to predict what the diffraction angle should be. And then here's their data. Okay, this is the intensity of the beam with angular position, and it predicted it and got beautiful experimental agreement. And all was right with the world. Electrons had a wave nature. All right, now, modern TEMs use this idea all the time, and they do it to generate something called a dark field image. All right, so this is the bright field image that I talked about before. Here's your objective. This is where your sample would sit, and then it passes through the objective lens to focus it onto the screen down below. Okay, so the objective lens starts to focus. Now, after the objective lens, there's an aperture or a pinhole. Okay. Where you position that pinhole dictates what kind of image that you're getting out. If you position the pinhole directly below the center of the lens, then you're getting the electrons that are not diffracted by the sample that it passes through to a great extent. And so that generates your bright field image. All right. Now, if instead you position your objective aperture off to the side over a conveniently located spot where you know diffraction is going to occur. Okay, so I've moved my pinhole here over to the side, and I know, for example, that I have a sample that's, I don't know, single crystal something, and I know what the angle of diffraction should be, and then I move my pinhole over so that it gets that wave rather than the straight pass-through wave that generates that bright field image. Okay? So I put it over here, and then that is used to construct my image. All right, so that's a dark field image. So the direct beam is blocked by the aperture, all right, while one or more diffracted beams are allowed to pass through that aperture. And since diffracted beams have strongly interacted with the specimen, then that gives you useful information that might be present in those dark field images. What useful information? Well, planar defects, stacking faults, particle size, crystalline structure, all kinds of things like that. Okay, So let me show you a dark field image as compared to a bright field image so you can see. So here on the left is a bright field image, all right? You have your nanoparticles, okay, on top of your grid or whatever, and the nanoparticles appear dark, so you know that the electrons were absorbed through those particles, okay? That's the bright field image. We've already explained that. Now here on the right is your dark field image. And you'll notice that you're getting structure out of the dark field image that you don't see in the bright field image. For example, look at this little boxed particle right here, okay? It just looks like a little circle in the bright field image. But if you look at over here in the dark field image, you see that there's brighter areas than others, okay? Now that's because the electrons that have passed through were more strongly diffracted by that nanoparticle on this side, right? So it appears brighter because the diffraction puts more electrons at that angle here than here. All right, and you can see that if it passes straight through, of course, the beam is not diffracted at all. And so that's why the areas that appear light in a bright field image appear dark in a dark field image, because there's no diffraction taking place if your electron beam is passing through nothing. All right. So this, by the way, was taken from a publication in the Journal of Applied Journal Physics D Applied Physics by Wellner and colleagues, and it was to examine the structure of these nanoparticles that they had fabricated. All right, now you can generate dark field images or pictures of your sample and get it that way. You can also generate the diffraction pattern itself, okay? So the objective lens, when it passes through the objective lens, you get a diffraction pattern that's automatically formed, all right, in a TEM. So the electrons scattered by the sample, and it combines them to generate an image in the image plane for a dark field image. But remember, the diffraction pattern and an image are simultaneously present, right? And just depends on the focusing of that intermediate lens, which appears in the plane of the second intermediate image and is magnified by the projective lens system on the viewing screen, that allows you to switch from real space, which is your image, to reciprocal space, which is your diffraction pattern. Okay, so this really makes more sense by looking at this picture here. Okay, so here's your specimen. It passes through the specimen and then goes through an objective lens. Okay, so you have your aperture here, okay, and then it passes through an intermediate lens and it focuses and forms the dark field image. Fine. Okay, now look here. Basically the same. Here's your specimen. Here's your objective lens, all right? You can see here, this is a diffraction pattern right here at the top, where the red line is at first, and then over here where the spots are. That's your diffraction pattern. It's where those beams from the electron beam converge again as they move through that lens. So if you focus on that, the pattern, instead of the image that's formed down here, then you see the diffraction pattern. So you can change the focus just by changing the strength of the lens. That's no problem. And if you do that, then what gets focused changes. So instead of the image, you're focusing onto the diffraction pattern itself. Okay? All right. Now, the acronyms that describe this are selected area diffraction, selected area diffraction pattern, and selected area electron diffraction. So they really can't settle on an acronym. If you see any of these acronyms, then that's what they mean. Now, the diffraction patterns look something like this. You might remember seeing them from Modern Physics 1. Okay, they can be quite beautiful, and they're patterns like this. If you have a single crystal, then they're going to be very, very ordered and make these beautiful patterns. All right? So you can get these from an electron microscope by careful preparation of single crystal systems, or focusing and choosing an area on the system that is a single crystal area. However, most materials are not single crystals. They have domains and they're polycrystalline. And when that happens, instead of the highly, highly ordered patterns, you get these rings of diffraction. Okay? And so you can figure out from the rings the spacing of the crystalline lattice and the structure. And you can calculate the lattice constants of your films. So that's 3 kinds of images that you can get out of a TEM, 3 most common. There's others. And like I said, if you find this subject particularly interesting, then you can go on and take our Advanced Microscopy course, and we'll tell you all about it in excruciating detail. All right. Anyway, I hope you enjoyed that, and I'll see you next time.